Alright, so let's move on to section 5.2, and here we're going to study waves formed by a spring. So, we're basically going to talk about transverse waves, and we're going to talk about transmission, reflection, inversion, fixed and open ends, and we're going to talk about the principle of superposition, which will be the only computation in this section, you could say. So basically, like I said, when waves travel along a spring, the velocity is uniform, as long as the medium doesn't change. Now, this is true if the spring is essentially suspended. If you're doing this on the ground, it definitely will lose velocity, so don't be confused if you're actually trying to work this out, because it will lose energy to friction. But if it's basically suspended, the velocity won't change too much. Of course, it's losing energy from air, friction in the air, but I guess you could say in a vacuum, the velocity would be uniform, essentially. So, let's talk about reflection. A couple points here. And if you have a Slinky, you can try this out if you have two people. If someone's holding this end, or if you fix it to a wall and you send a transverse pulse at it, it comes at it, hits this part, what will actually happen is it will reflect, and it will reflect and invert, right? It will hit the wall and invert. Why it does this is purely, you could say, geometry almost, or collision theory in a sense, because as this comes in, the points here as it hits the wall will kind of reflect almost like this. Okay, if this came in, it will reflect downwards. Very similar. It just, all the points will do this at the same time, and in unison they'll be inverted. If the end is open, however, okay, it won't be able to do this collision because it's open. So when it's that, it actually does not invert. It stays what you'd say upright. So this is an inversion, and this is no inversion. Oh, I'm running out of room, sorry. No inversion. This blasted program never shows me if I'm cutting off or not. Or you could say it stays upright. Okay? Simple enough. And I might actually link in the Moodle, I'll link a Java applet that lets you kind of play around with a digital Slinky. Of course, it's actually it's very useful. So I'll put that up there so you can kind of experiment with that. So now let's talk about interference. What happens when you send two waves at each other? Okay, this is important for a slew of applications, okay, including noise canceling devices such as headphones or microphones, sending radio waves to your car or to different devices, including Bluetooth. It's important to understand how waves are affected when waves hit each other. If you think about it, waves are always hitting each other, particularly if you're at school where most people have phones. These text messages are sent, okay, in waves. Almost everything is sent in an electromagnetic wave, some kind of wave that will carry some data. So they're always passing through each other. So what happens when they pass through each other? By the way, if they couldn't pass through each other, if they always collided, then all of our electronics would be practically useless. So this, our first point in section 5.1, talking about how waves pass through each other, is very important. Now, when they hit each other, the interference they'll form is either constructive or destructive interference, or a bit of both. Basically what happens, if you have, let's suppose these two waves hit each other and they're the exact same, okay? Because they're in the same orientation, they will actually, what you basically do is you're going to add their amplitudes, okay? So here, if this point overlapped with this point, you would add their amplitudes to get twice the amplitude. Similarly, you do the same thing here. Twice the amplitude. So it grows bigger, basically, if they're the same orientation. So if two waves hit and they're in the exact same phase, they'll construct. This is called constructive interference. Destructive interference, if they're the complete opposite, in this case, they cancel each other out. But notice how you're actually still adding the amplitudes, because this amplitude adds to this amplitude to give you nothing. So that is the key word, add the amplitudes. That's how you do this, amplitudes. That is how you understand the principle of superposition. This is, of course, destructive interference. Okay, so a couple more pictures talking about this. By the way, the point where the maximum amplitude occurs is called the antinode. So that would be these guys, maximum amplitude. The point where there is no motion, okay, or the point that crosses the horizontal axis is called the node, which would be these guys, okay, or here. Here are the nodes. Here are the antinodes. Okay. Now, let's do some problems. So you have to imagine that this wave is coming in this way, this wave is coming in this way. I walk you through these examples. So these two I'm not going to do for you here. I walk you through them through these steps. Basically what you're going to do is you're going to use the grid and you're going to mark where the two waves overlap. Okay, I mark it here in green. That's where they overlap. Over here there's no overlap, right? So nothing, no interference will happen there. Here's the points, this shaded region here is the interference. That's where you're going to have, in this case, you're going to have a cancellation because they're on opposite sides. But basically all you do is you're going to pick points. Okay, place a reasonable amount of points on the overlapped line. So here I pick some points, as you can see, all these guys. And basically what you're going to do is you're going to identify where they are in relation to the horizontal line. So here's the horizontal line. I'm using these grid points here, that this is about 0.1 of the first grid up. Here this is one's 2 squares up, that's why it has a 2. Do that for all of them, and this is going to be negative, and this is going to be a positive area. In step 4 and 5, in step 4 you basically will just add these values. 0.1 from the horizontal, this is negative 2, so you add that to get negative 1.9, which is this, so that will be where you plot the new point, which comes right there. So basically it just pushed this, it pushed that one up this much, that much over there. You do this for the whole thing and then connect the dots. That's what step 5 is. This one in yellow is the resultant wave. This is what this wave would look like if you took a snapshot of these two waves interfering at this point. This will happen in a matter of milliseconds if you were to actually do this with a Slinky. If you actually could have a slow motion camera, you would see this frame like this. As it kept moving, of course it would morph into different directions and different shapes, which is why that applet that I'll link you to is pretty useful. So I did the second example and I think this is it. 2 more. Okay, so I'll finish off, I'll do these ones with you. So identify the spot of interference. Well, here and here, right? In this practice problem, identify the spot of interference. So that's the spots. Now I'm going to put some points on that would be easy to kind of evaluate. This point's pretty easy. I'll choose this one. You have to choose corresponding points on both curves. This point might be pretty easy. Choose this one down here. Okay, I'll choose those 5 points. On the curve, the corresponding points will be this one. This one has they have the same vertical coordinates, horizontal coordinates actually. Okay. Now I'm going to add them. Do them blue. You can either do this. You can identify what numbers these would be. So this would be +2. This would be like 0.2. So the resultant will be about 2.2, which would be roughly around here. Okay, this is going to grow bigger, but they're both on the same side. Eventually you can just do this by looking at how big this is and kind of adding that much up here, which is what I'll do now. If you want an algebraic way of doing it, you can look at the previous example. An artistic way of doing it would just be to look at this. This is about 0.8, by the way, and you would add that distance to this. Of course, if you do it algebraically, this is about what, 2.6 maybe. This is about, sorry, this is about 0.8. So the addition there, you're going to get like 2.4, which is exactly where I do this. Okay, so you can either do this with just by your vision, or you can do this by using algebra. So, or addition, sorry. So this is going to double, give you that much. And this one will grow just a bit. And then they'll turn the same. I'll trace it in, well, I guess I'll trace it in black. So this will grow right here. So the answer's in black right there. So you actually can do this rather quickly. Here, this is the interference is, I mean, they're a bit tedious. There's the interference and it starts right there. So what happens here is you're going to have destructive interference. If you want to label this, by the way, this is clearly constructive. And this one's definitely going to be destructive. The reason you know that, by the way, is because it's in the opposite side, so they're going to get smaller here. If you pick some points, you can pick this one because it's on the grid, this one because it's on the grid, this one is the same thing. So if you pick those 4 points, this one maintains its position. By the way, I'm comparing it to this point, comparing it to this point, comparing this one to this point. Okay? And once again in blue, I'll just do the result. The result of these two, this guy, by the way, if you want to do this, this is about negative 0.2. This is about 2.3. So the result will be, if you add those together, 2.3 plus negative 0.2, you're going to get 2.1, which will be right here. And notice how that distance, you just decrease it by that much. Same with this one. Look at this distance right here. You're going to decrease this one by about that much. Same with this one. Look at that distance, decrease this one by about this much. So because I've done this quite a bit, once you get the hang of it, that's why you can do it this way. Once you connect it, that's what we'll be left with. So in blue this time, that's the curve. Destructive interference. Notice how it got smaller. Destructive. So that is the principle of superposition. Now, let's finish off this video by talking about standing waves. So a standing wave will be when two waves are basically interfering, but it's difficult to tell if there's two waves. Okay? And this example is actually a bit annoying because it's a three-dimensional. Okay, this is kind of circling around like this. Let's take a look at this picture. When you look at it, how many waves is there? A standing wave is when it just so happens that one of the waves, which I'll draw for you, here's one. My tracing abilities are a tragedy. I apologize. And here comes wave 2. Now you see what a standing wave is. So it's kind of lucky, isn't it? It just is when the nodes hit the nodes and the antinodes hit the antinodes. Okay, so nodes to, what in the world is that? Whoa, that's not how you spell nodes. Sorry. And nodes. So, you know, when you can make a standing wave, if you were to, you know, with someone else, swing a slinky between each other, okay, you'll know when you hit a standing wave because both of you will basically feel no resistance, okay, because you're both aligned in your frequency, okay. So, now that you recognized that there are actually two waves on top of each other here, the question is saying using measurements taken directly from the diagram below, determine the speed of the waves if they move from the start to end, here's the start, here's the end, in 3 seconds. And for this digital video, we'll say that each square is 1 centimeter. So, you need to find the velocity, and velocity is equal to wavelength times frequency, right? We are given the time from start to end. So it actually might be easier here to use distance over time because you have the total time. But that means you need to know the distance from here all the way, to here. Okay? You need to know that. In other words, you need to count, or you could take the wavelength and multiply it by how many waves you have, which is what I'll do. But a wavelength is actually the distance from here, not to here, but to here, right? In phase points, which means we have 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, 8.5. Okay, so a wavelength here is 8.5 centimeters, which means the total distance, delta D, will equal 17 centimeters because you're going to multiply that by 2. So you're going to have 17 over 3, which comes out to be 5.66. We'll go to 2 significant figures to give you 5.7 centimeters per second. Okay, so that is section 5.2. Some drawing, some theory, and some calculation here with waves in a spring.